Welcome back. From a statistical study, often referred to as inferential statistics, we can deduce several key insights, including patterns and trends, how variables behave, change over time, or relate to one another, relationships between variables, whether variables are associated, and the strength and direction of those relationships, differences between groups, whether observed differences are likely meaningful or due to random variation, magnitude of effects, how large or practically important an effect is, not just whether it is statistically significant, uncertainty and reliability, how confident we can be in the results, usually expressed through confidence intervals or margins of error, predictions and forecasts, reasonable estimates of future or unseen outcomes based on observed data, limitations and assumptions. What conclusions are valid given the data quality, study design, and model assumptions? Together, these insights help transform raw data into informed decisions, explanations, and evidence-based actions. Let's start with the confidence interval on single sample. We have so far covered all the required background, descriptive statistics plus basic probabilities to start doing some serious statistics. The starting point of inferential statistics is the confidence interval for one sample, which is easily developed for hypothesis testing, and ANOVA, which shall be covered in the next chapters. The first application is the point estimate. Figure 7.1 presents the procedure of a point estimate. We start by collecting a sample from a population, and we calculate its statistics like the mean, variance, and proportion. Finally, we infer these statistics to the population. Nonetheless, regardless of the population value being estimated, there is always a sampling error. Therefore, by definition, the point estimate represents a singular value, or a statistic, calculated from sampled data and used to estimate a population parameter by using the mean, the variance, and other statistics. Let's start with a simple example. Suppose we are asked to estimate the average age of the male student at a local college. Therefore, we selected a random sample for this college and calculated the average age to be 22. This sample mean of 22 can be used to estimate the population mean, mu. Put differently, estimate the average age of all male students at the local college. The sample mean of 22 is called a point estimate of the population mean, mu. Because a point estimate is a unique value, we can't tell how well it represents the true population parameter. Therefore, in inferential statistics, we refer to an interval or range of values to estimate the exact value of the population parameter. Suppose we collected several samples and calculated the sample mean for each sample. We found the age of male students at the local college lies between 20.5 and 23.5. This range of values is an interval estimate, which we refer to as the confidence interval. Therefore, by definition, a confidence interval uses sample data to provide a range of plausible values for a population parameter, such as the population mean, population standard deviation, or population proportion. As examples, we may be 95% confident that the population mean mu lies in the interval -0.2 to 2.6. We may be 99% confident that the population standard deviation, sigma, lies in the interval 1.5 to 12.8. Finally, we may be 95% confident that the average height for men in the United States lies in the interval 5.8 to 5.9 inches. It is important to distinguish between a point estimate and a confidence interval. Figure 7.3 in the textbook shows the difference between a point estimate and a confidence interval in inferential statistics. Let's do another example. Polling organizations frequently conduct polls investigating public opinion on how the president is performing his duties. Such polling organizations publish a presidential approval rating. Let's use the parameter P to represent the population approval rating. Suppose that in a telephone poll of a sample of 1,000 adult Americans, 430 said they approve of the way the president is handling his job. P hat is the sample approval rating. P hat equals 430 divided by 1,000, or 0.43. How close is the population approval rating to the sample approval rating? In other terms, how close is the statistic P hat to the parameter P? We are not going to be able to say with certainty how close P is to P hat, because P is unknown since we cannot poll the entire American adult population. However, we can express how close we feel that the P hat value is to the true value of P. This is the objective of the confidence interval. We frequently express our uncertainty in the exact value of the parameter with a statement like, the poll is believed to be accurate to within 0.03 margin of error with a confidence level of 95%, meaning that P lies somewhere between P hat minus 0.03 and P hat plus 0.03. Therefore, we may be 95% confident that the population approval rating lies in the interval 0.4 to 0.46. Let's introduce another important term in statistics, the standard error. The standard error is a measure of how different the population mean is likely to be from a sample mean. It indicates how much the sample mean would vary if new samples were collected from the same population. How to interpret the standard error? Since a sample statistic will never perfectly match the population parameter, the standard error indicates how representative a sample is of a population, hence helping make valid conclusions. A high standard error shows that sample means are widely spread around the population mean. This indicates the sample may not closely represent the population. A low standard error shows that sample means are closely distributed around the population mean, indicating that the sample is more representative of the population. Let's introduce another important term in statistics, the standard error. The standard error is a measure of how different the population mean is likely to be from a sample mean. It indicates how much the sample mean would vary if new samples were collected from the same population. How to interpret the standard error? Since a sample statistic will never perfectly match the population parameter, the standard error indicates how representative a sample is of a population, hence helping make valid conclusions. A high standard error shows that sample means are widely spread around the population mean. This indicates the sample may not closely represent the population. A low standard error shows that sample means are closely distributed around the population mean, indicating that the sample is more representative of the population. How to estimate the standard error of the mean of a population? It can be done with 3 easy steps. Step 1. Find the population mean. Step 2. Find the population standard deviation. Step 3. Find the standard error of the mean. One last definition before we start exploiting inferential statistics. The margin of error represents an expression employed to determine the percentage point by which the sample mean will differ from the real population mean. A higher error indicates a significant probability that the outcome of the sample reported may not represent the exact reflection of the population. When doing serious statistics, the population variance may be known or unknown. Therefore, the computation of the margin of error may be a bit different if the population variance is known or unknown, or if we are estimating the population variance or the population proportion. Let's address each case separately. Enough definitions, and let's do some statistics. As it was mentioned before, the true population mean is usually an unknown and exact number. We're going to use statistical techniques to guess this number with a certain level of confidence. In the previous chapter, we have established that by taking a sample that is large enough, n greater than or equal to 30, we can use the central limit theorem to assume that the sample mean is normally distributed as shown in the figure. By taking a sample that is large enough to satisfy the central limit theorem, we can be 95% confident that the true population mean, mu, belongs to an interval between the sample mean minus the margin of error and the sample mean plus the margin of error. For instance, for a confidence level of 95%, the significance level is alpha equals 0.05 and alpha over 2 equals 0.025. Figure 7.5 shows the area of alpha over 2 equals 0.025 in each tail of the normal curve. The z-value is then z of alpha over 2 equals 1.96 from the z-table. Note that the cumulative area to the left is 0.025 from minus z of alpha over 2 equals minus 1.96 and 0.975 from z equals 1.96. To conduct a confidence interval test on a population mean, knowing the population variance, follow these simple 4 steps described in the following cheat sheet. Step 1. Read carefully the problem statement and extract the statistics, such as the sample population, the sample mean, the population standard deviation, and the confidence level. Make sure that the problem statement states that the sample is normally distributed, or you may check the normality by using the central limit theorem. Step 2. Get the critical value either from the z-table or by using Microsoft's Excel as shown. Step 3. Calculate the margin of error by using the simple formula shown. And finally, step 4. Write a concluding statement like, "We are 95% confident that the true population mean is between the sample mean minus the margin of error and the sample mean plus the margin of error." Let's do a confidence level example. The problem statement states, exam scores are normally distributed with a population standard deviation of 5.6. A random sample of 40 scores on the exam has an average of 32. Estimate the population mean with 1. 80% confidence, 2. 90% confidence, 3. 98% confidence, and, more importantly, 4. Draw some conclusions. To solve this problem, follow the 4 simple steps. Step 1. Extract the statistics from the recorded data and check normality. Step 2. Get the critical value from the z-distribution table, or by using Microsoft's Excel. The normal table gives a z-score of negative 1.28 on the lower tail, and because of symmetry, 1.28 on the upper tail. Step 3. Calculate the margin of error given the simple formula and find the lower and upper limits of the confidence interval. Finally, step 4. Conclude with a statement. We are 80% confident that the population mean score is between 30.87 and 33.13. Question 2. Let's redo the problem with 90% confidence level. Step 1. Record the data or check normality. Step 2. Get the critical value like before to find a z-score of 1.645. Step 3. Find the margin of error and calculate the lower and upper limits of the confidence interval to find mu between 30.54 and 33.46, as shown in the slide. Finally, step 4, make a conclusion. We are 90% confident that the population mean score is between 30.54 and 33.46. Following the same method, let's do question 3 having 98% confidence level. Step 1. Check the data and check normality. Step 2. Get the critical value by using the z-table or Microsoft's Excel to find a z-value of 2.33. Step 3. Find the margin of error as shown in this slide. Finally, step 4. Conclusion. We are 98% confident that the population mean score is between 29.94 and 34.06. In question 4, it gets interesting. Let's put all these results on a table and compare them to draw some conclusions. We can see that as the confidence level increases, the critical value increases, the margin of error also increases, and consequently, the confidence interval becomes wider. Let's work another example. The ratio of the length of the second digit, index finger, to the fourth digit, ring finger, is often referred to as the 2D to 4D ratio and has drawn much attention from behavioral researchers. A study investigated the 2D to 4D ratio within a sample of women of European descent at a university. A sample of 135 women yielded an average 2D to 4D ratio of 0.988. What is a 95% confidence interval for the population mean? Assume that the standard deviation of the population is sigma equals 0.028. Following the cheat sheet provided in the textbook, let's solve this problem. Step 1. Extract the statistics and check normality. In this case, normality is assumed thanks to the large sample. Step 2. Get the critical value. Z-value from the standard normal distribution table. Step 3. Find the margin of error. The 95% confidence interval for the population mean is between 0.983 and 0.993. Finally, the most important step. Step 4. Draw a conclusion. Therefore, we can be 95% confident that the mean 2D to 4D ratio for women of European descent at this university lies within the 0.983 to 0.993 interval. However, this conclusion applies only to the population from which we sampled, and any time our sample is not a random sample from the population of interest, there may be biases present. Now, to better understand the confidence interval procedure, let's investigate the factors that affect the margin of error. In other words, what can we do to reduce the margin of error? What are our options? Let's use the confidence interval formula for mu as shown. The confidence interval is affected by A, the standard deviation for the population, sigma, B, the sample size, n, and C, the confidence level, 1 minus alpha, is produced thanks to the standard z-values. Let's investigate each one of these effects on the margin of error. A, effect of the standard deviation on the margin of error. By observing the margin of error formula shown in the slide, we can see that it is proportional to the standard deviation sigma, since sigma is in the numerator. So, if all other factors are equal, a doubling of the standard deviation would result in a doubling of the margin of error. This is illustrated in the following figure of margin of error versus standard deviation sigma, which is a linear relationship. A, effect of the standard deviation on the margin of error. By observing the margin of error formula shown in the slide, we can see that it is proportional to the standard deviation sigma, since sigma is in the numerator. So, if all other factors are equal, a doubling of the standard deviation would result in a doubling of the margin of error. This is illustrated in the following figure of margin of error versus standard deviation sigma, which is a linear relationship. One of the best ways to compare statistics and to draw conclusions is in table format and a graphical plot. The table shown contains all the statistics, and the plot shown the linear relationship between the standard deviation and the margin of error. The margin of error is linearly proportional to the standard deviation. This is obvious since the variance is synonymous with uncertainty, which implies a wider margin of possible values, and hence of errors. Now, let's see the effect of the sample size on the margin of error. Recall that the greater the standard deviation, the greater the uncertainty, and the more difficult it is to catch the exact value of the parameter of interest. Therefore, the greater the margin of error. Let's look at the effect of the sample size n on the margin of error through the relationship shown in the figure. Notice that the square root of the sample size is in the denominator. So if we want to cut the margin of error in half, we need to quadruple our sample size. The following figure illustrates the relationship between the margin of error and the sample size. If the sample size is increased from 20 to 200, for example, there is a significant reduction in the margin of error. However, an increase in the size of 600 to 800 does not decrease the margin of error by a similar proportion. The greater the sample size, the more information we have and the more precise we will be in detecting the parameter of interest, and the smaller the margin of error will be. However, notice that this relationship is not linear. Let's do an example to illustrate the effect of the sample size on the margin of error. Assume that we have a sample with the following statistics: sample mean of 80, standard deviation sigma equals 20, and a z-value of 1.96. Question 1. Find the margin of error, its lower and upper bound, for sample sizes of n equals 10, 400, and 800. Question 2. Conclude the effect of standard deviation on the margin of error. Let's calculate the margin of error and the lower and upper bounds of the confidence interval and put these statistics on a table and a graphical plot. As you can see from the plot, the margin of error decreases rapidly by increasing the sample size. However, keep in mind that making more observations to increase the sample size is expensive and time-consuming. Finally, what is the effect of the confidence level on the margin of error? Recall that the confidence level is related to the z-value. For a 95% confidence level, z equals 1.96. For a 99% confidence level, z equals 2.576. Therefore, if we want greater confidence, we are going to have a greater margin of error. Look carefully at this plot and notice that beyond a 95% confidence level, the margin of error goes up rather quickly. That's the reason why, in the most practical situation, we choose a 95% confidence level, which provides a good balance between high confidence and a reasonable margin of error. Let's do the following example. Determining the required sample size, n, for estimating mu. Let's estimate mu within an amount m with 95% confidence. How large a sample size is required to estimate mu within that amount m? Let's have a look at the solution. Estimating mu within m is the same as wanting the margin of error to be no more than m. So knowing m and sigma, let's do some algebra to find the sample size. We may want to change the confidence level by finding the corresponding z-value. So the sample size n must be at least the value shown in the slide. Let's do another example, determining the required sample size for estimating mu. Assume that we are sampling from a normally distributed population with sigma equals 65. 1. How large sample size is required to be if we wish to estimate mu within 4 with 95% confidence? 2. How large sample size is required to be if we wish to estimate mu within 4 with 99% confidence? Let's have a look at the solution. Step 1. Let's use the sample size formula. Step 2. Find the formula parameter values for the sample size. Remember that we need a sample size of at least as many as 1014.422. The sample size must be a whole number, so we must round up the value found. Therefore, the minimum sample size is 1015. For question 2, let's use the same method. Step 1, let's use the same sample size formula. Step 2, find the formula parameter values to find that we need at least 1,753 observations. Finally, in step 3, let's verify and discuss the results. By increasing the confidence level from 95% to 99%, while keeping the same settings, the required sample size increased considerably from at least 1,015 observations to at least 1,753 observations. As was mentioned before, having such a large number of observations is quite expensive and time-consuming. Therefore, this formula is typically used as a rough approximation. The population standard deviation, sigma, is usually not known. We may have to use some adjustments to find mu in the next section. I hope that you have well understood the confidence interval procedure on a single sample, knowing the population standard deviation, sigma. In the next video, we shall discuss confidence intervals of a population mean having sigma unknown. Check our textbook, Illustrated Statistics for College Students, on Amazon. Details are on the description. Thanks for watching.